Welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today's topic is on the fuse, and it all starts now. All right, welcome to another IAEI News Live. This is incredible. Today's discussion, I think you're going to enjoy it. I'm going to enjoy it. I know the fuse is one of those solutions that we use, but I don't know that we fully fathom the power of the device and its capabilities. And once you understand some of those capabilities, I think we can strategically use this device in a power distribution system to help achieve goals. So this session is, again, we're following the process here. We're establishing a series of videos on specific topics. We've covered the circuit breaker, the panel board. Now we're covering the fuse, and this is a fuse fundamentals. Some of us call it fuseology, if you're familiar with that term. So I've got MobiCam set up so we can take a look at some of the labeling, and I've got some products here in my possession that we can take a look at and help you understand, even some relay technology to help you understand how we achieve some of the requirements that are associated with fused systems. Okay, so let's get this party started, right? Fused fundamentals, and this is an international association. This is the IAEI. If you are familiar with the IAEI, I think that that this is one of those organizations that's a great umbrella that many different types of electrical professionals all work in and under. Whether you are a design engineer, electrician, electrical contractor, electrical inspector, mechanical engineers, if you're in the building trade, if you do anything that uses electricity, this is a great organization to be a part of, because we help you understand the National Electrical Code. We help you understand standards, whether it be Underwriters Laboratories, UL standards that govern the development of products, standards that help you use electricity safely. So membership has its value. I would ask that you not only subscribe to this channel. This is a free video. We're going to do 1 hour on fuseology. Please remember, subscribe to this channel. I don't know if I have it here. Nope. Subscribe to this channel. Also, be a member of IAEI, because in the future, and as we develop and grow our online experience, I'm going to be offering some in-depth industry. We're going to get some industry experts open to IAEI members. So please, membership has its value. The link for membership is down below. Also, I will remind you, purchase your copy of Analysis of Code Changes. A lot of what I discussed today is going to be focused on the 2020 version of the National Electrical Code. The code that changes, the IAEI puts together a book, Analysis of Code Changes, every code cycle. The uniqueness of this book is that they pull together all of their members who sit on every code making panel, develop this industry resource, and they help you understand some of the most important changes that occur in the National Electrical Code. And they give you some in-depth review of those changes from the people who are sitting on the panel. That is a huge point. The value of actually being at the table and to be able to capture what you saw and what you heard, or what was seen and what was heard by that individual, and capture it in this book, is a resource for you. That's something that I don't think anybody else can supplement. If you're not sitting at that table, if you're not part of those discussions and those debates, you can't bring that extra added icing on the cake with regard to these changes. So you're going to want to get your analysis of code change. And it can, if you're not on the 2020 code, if you're on an earlier version, reach out, go out. There's a link down below. You can still purchase some of those older references. So please feel free. And if you, and membership has its value. If you're a member of IAEI, you get a discount on those resources. All right, so let's talk about the fuse. Now, I will point out, when it comes to definitions, and I was surprised to learn this myself, Article 100 has definitions, and you'll notice that there, in the 2020 code and earlier codes, there are different parts. In the 2020 code, we have part 1, which is general, and if you look in general, there is no definition of a fuse. I was surprised to see that myself. There are definitions of a lot of things, circuit breakers included, but no definition of a fuse. For you to get to a definition of a fuse, you've got to move over to part 2, which is focused on over 1,000 volts nominal. Now, let's take a look at what the National Electrical Code says. It's on page 70-41 on your version, your copy of the National Electrical Code. A fuse is an overcurrent protective device with a circuit opening fusible part that is heated and severed by the passage of overcurrent through it. So what we know is that we are heating an element. When current passes through it, we know current generates heat, and it will sever the element. And I'm going to show you an element. This is an example of an element that's inside of a fuse. And we're going to talk about this. You're going to understand what this is as we progress through this discussion. Now, there's an informational note. A fuse comprises all the parts that form a unit capable of performing the prescribed functions. It may or may not be the complete device necessary to connect it into an electrical circuit. That's important because I'm going to bring up a fuse here, but it's going to be green. And I'm going to show you. Let's do this. Let's do this. All right. So what I'm going to do is I'm going to show you a fuse, and I want to help you understand what we mean by the fact that you just can't place a fuse inside the circuit. So this is, I got MobiCam, Mobi1 Kenobi up. So this is a fuse, and if you'll notice, this fuse has blades on it. There's no place on this fuse for us to connect a wire. There's no termination on it. There's no terminal on it. Here's another fuse. Okay, this is sort of a typical fuse that you might see. Just a cylindrical tube, ferrules at either end. There's no possible way for you to connect a wire onto these devices. What this informational note reminds us of is the fact that we will probably need a block, a fuse block, to get rid of that. There's the subscribe. There's the subscribe. Don't forget to subscribe. I don't know how to get it off now, but anyway. So let's get rid of studio mode. There you go. So This is a fuse holder. I'm going to pull this fuse out. So this is a fuse block. And you'll see there's a terminal in here. This is what you need. This is what this informational note is talking about. It says a fuse comprises the parts that form a unit capable of performing the prescribed functions, which is opening. That's not what this does. It says it may or may not be the complete device necessary to connect it into the circuit. So most fuses require a device like this, which is we call these fuse blocks, fuse holders, that enable you to insert this into the circuit. And we're going to talk a little bit about this, but we'll probably have a separate section as we dig deeper into fuses and fusology and the proper uses of fuses. So remember that, and I am going to slide this back into the jaws of life. There we go. All right. And we'll talk about fuse holders a little bit in this, but we want to focus on the fuse. Now, I will say, as I look through the different definitions under fuse, they have controlled vented power fuses. This is why it's in the medium voltage section. Expulsion fuses, medium voltage fuse. Non-vented power fuse unit, and vented power fuses. Most of those are specific to medium voltage applications. All right, so, and there's your, and then another fuse is the electronically actuated fuse. Now, you'll say, Tom, when would I have the need for an electronically activated fuse, and what is an electronically activated fuse? Well, I'm glad you asked that question. 240.67 talks about the methods to reduce incident energy. Now remember, 240.67 is titled arc energy reduction. And just like in 240.87 for circuit breakers, 240.67 has requirements for large fuses, 1200 amps and above, to have a method to reduce incident energy. Now, one of the options is a current limiting electronically actuated fuse. So you could have, and in this case, there's the definition of an electronically actuated fuse is an overcurrent protective device that generally consists of a control module that provides current sensing, electrically derived time current characteristics, electronically, energy to initiate tripping, and an interrupting module that interrupts current when an overcurrent occurs. Electronically actuated fuses may or may not operate in a current limiting fashion, depending on the type of control selected. And this is for code panel 10 definition. Now, I will say that these devices typically leverage what we call pyrotechnics, where they'll put a charge on the element or inside that unit, and then you hit it with a control voltage, say a low voltage 24 volt DC or something of that nature, and it actuates and sets off this small charge, which opens the fuse. So that's an electronically actuated fuse. Now let's get into what's the secret sauce, so to speak. What's in the tube that does the work that it does? That's this device right here. So what you're looking at up there is basically this device. Flip it this way, like this, right? So there's the overload element, and these are the short circuit elements. That's what it looks like. Now, this device here is what does the work to open the circuit. And depending upon the fuse, so in this fuse here, it is a cylindrical. That's typically the way this is put in. In some cases, you might have what we call a cube fuse, which is a square fuse, which is a little different format, but this element resides in this fuse just like that in a different configuration. In fact, think I have it. Thought I did, but I don't. I thought I had a see-through, but in any case, this is the device. This is how it does its work. And there's a little bit closer of a view. Now, this overload element that's right here above my head, this that element is basically, move my drawer in, that element handles the overload, and then the pinch points in the meat of the long rectangular portion of this element is what handles the short circuit currents. Now you got to remember, what I'm not showing is that this element is completely surrounded with sand. And the sand, remember what happens when you heat it. It turns into glass, or what we call fulgurite. I'm not trying to be vulgar with you, but that's what it is. So fulgurite. And what the sand does when it heats up and it turns to fulgurite, it adds that insulation to help insulate and isolate to ensure current doesn't flow. So that's basically what the fuse element does and how it operates and functions. So on the overload, think of what I'm showing here is I'm showing that you have a pinch point, or a how would you call it? It's a tiny pin that's there's tension on it based upon a spring, and that pin, when heated, can be melted. Hence, what we're showing here is that the pin is separating. It's together up top, and then it separates down the bottom when you heat it. And what does it take to heat and melt that element? Current and time. So on overloads, if I let higher currents flow long enough, I can melt that element and have it open. And I'll show you what that means on the trip curve. Keep in mind that as long as my current, my normal currents, are lower than the rating of that fuse, I'm not going to melt that element. Hope you understand that one. Now, this is the short circuit. What happens during a short circuit? Very high fault currents flow through the device, and each of these little tiny pinch points, each of those little tiny pinch points explode. And what we're showing on this bottom one right here is we're showing the sand that turns into fulgurite that's insulating these units. And I do have a spent fuse around here somewhere. Let's see if I can put this on MobiCam. Mobi 1 Kenobi. So this is a spent fuse. That's what it looks like. This is an actual spent fuse. This is what it looked like before, and that is what it looks like now, after it has seen a high short circuit event. All of that sand that was in there basically turned into fulgurite and helped insulate every one of those pinch points. Look at the difference between these elements. That's what it looked like before, and that's what it looks like after. And you'll notice there's two elements in here. So there's reasons for the number of elements, and it has to deal with the voltage levels, and we have to deal with how much current that we want to pass through. But that basically is what happens to a fuse inside when it does its job, and it gives its life for you and me and the conductor that it's protecting. All right. Now, what all of this translates into, what I just showed you, this thermal end. Now, this element, this is the way it's in this picture. I got to get my Keith Laughlin thinking pen. This portion up here is the overload region, up here. These pinch points and that short circuit protection is down here and this way. When the fault current is way higher than where it crosses 0.01 seconds, way up in this region. And I would say probably arguably somewhere even along this portion of the TCC curve. But way up here in this region, this is the area when I get fault currents way up here, all of these pinch points, like in the case of this fuse here, when those pinch points, this saw a lot of fault current well into this region of the trip curve. And all of those pinch points were activated. Now, in some cases, if you ask the manufacturer, they could probably give you a ballpark figure based upon how many of those are gone and what that element looks like. They can tell you sort of the range of current that it saw. And if you think about it, if you send in a fuse and you say, look, my fuse opened and I'm not sure why, and we look at this and all of these pinch points are intact and just this element has been opened, we could pretty much tell you that your current was probably in this region right in here because you were in the long time portion of the trip curve. So I could probably tell you a ballpark of how much current you probably saw by looking at the element. And what we'll typically do is X-ray these devices. So you could, if you really want to understand how much current is being seen by a fuse when it opened, you could ask for a little X-ray and see what happens, and we'll give you a ballpark figure. All right, so let's move on. Now the sand, you shake these devices. In some cases, you might hear, like I hear a little bit of sand, a movement in this one. I don't hear any sand movement in that one. I don't hear any in this one. The sand, what does it do? Well, it does a lot more than just what we explained here by turning himself into fulgurite. It helps cool the element as well. Because, think about it. You're heating an element inside and you have a material around it that helps absorb heat. So it can help cool the fuse. And it also, that when that fuse opens, the fulgurite can help isolate the fuse after the operation. So basically make sure the current does not flow through the device. Boy, these glasses, man, give me a little dinko on here. It restricts the arc. So if you think about this element, which I'm not sure what I did with it. If you think about the element, and I lost my element. I'm out of my element. I don't know what I did with it. But if you think about that element and the fact that all of those pinch points will open, I lost my element. What the heck I did with it? This is what happens when you have a messy desk, I guess. So each one of those pinch points, when you have the sand around there, around that element, when it opens, it will help contain that arc because it's an insulating device. It will help contain the arc and restrict it around the element itself. And that way it helps regulate the voltage, the arc voltage. And that's that voltage when you draw an arc, the voltage across the arc. All right, there it is. Man, put it over there. So think about this element surrounded in sand, and every one of those pinch points are covered with a sand. and the current will flow through these tiny pinch points, but when they open, that sand is there to help absorb the heat, contain the arc, and facilitate the isolation. Now I'm going to put this right in front of me so I don't forget where it's at. Now the fuse body. The fuse body itself is what contains the arc, and I have the same materials here. But in any case, the fuse body can vary, and I don't have a high-speed fuse, but I do have some pictures of high-speed fuses. The materials that are used are designed to be able to handle the pressures, any pressures and gases and whatnot. There's not going to be any gases, but that are contained inside. In some cases, the fuse body can help cool the fuse itself. This is a KRPC fuse, Class L fuse. This is a 1200 amp fuse. It's got a material on the outside that's it's a very hard material. It helps cool and contain all of the materials that are inside. It can be porcelain. It could be some sort of fiber. So the materials that are used to help formulate and hold the fuse and contain the fuse, like this is a cube fuse. It's more of a thermoplastic type of enclosure, so to speak. So very durable, and again, they provide the method to hold everything together. Now, let's talk about what you'll notice in these are, I've got two fuses here. And what I want to show you is across the top here. This is these are both the same type of fuse. This is a catalog number, LPS RK. This is 100 amp and this is 200 amp. You'll notice the size difference here. Just look at the ends of the blades. Okay, this blade is shorter than this blade. This blade, these two fuses are not the same size fuse. So what we know is, just like a circuit breaker has frame ratings, fuses will have sort of frame ratings. And they pretty much align with the switches and whatnot that they will go into. Remember, we said we have holders, and a typical fuse holder will handle a range of fuses. And this is, for example, is a 100 amp fuse, and it won't just hold a 100 amp fuse. It can hold fuses rated lower than 100 amps. So the size of the fuse will be different, and you'll notice the format. Now I got a green screen going on, so all I'm interested anyway are the ferrules, one at either end. You'll notice this is a tubular and this has blades. Okay, the holders will have to accommodate these, and the size of these are standardized. So when you hear a Class CC, I nicknamed that Charlie Chaplin because of the little dimple at the top. That's way over there on the right or on your left. It's the CC fuse. You'll see those on control power circuits, in control transformers and things of that nature. Little PTs, control power transformers. You might see them in street lighting fixtures. You'll see them in holders that look like this. This is a DIN rail mounted holder with the little door on it. And I don't think I have any fuses in these. No, I don't. So you would typically put your fuses inside here, and this is a CCP, what they call it, and then this is a specific catalog number, but it'll tell you what types of fuses. These are CC fuses that go in this. So that's that Class CC. These are smaller fuses. You'll see these in industrial control panels. You'll see these on transformers and things of that nature. convenient, and this is a DIN rail mounted holder. So each of these fuses will have their own holders. The cube fuse has its own holder, right? So here is a holder for a cube fuse. Here is a cube fuse. So this is a 60 amp cube fuse holder, and I'm going to see what this fuse rating is here. This is a 30 amp fuse, and it fits in a 60 amp holder. Okay, so this holder, although it's rated for 60 amps, it can hold fuses smaller than that. And fuses will typically have rejection features, unlike circuit breakers. Circuit breakers don't have rejection features. I can put a 20 amp circuit breaker in the same slot as a 60 amp circuit breaker, single pole. I could, as a 10 amp circuit breaker, as a 15 amp circuit breaker, as a 10K interrupting rating, as a 22K interrupting rating. They all fit in the same slot. You don't have that same type of flexibility when it comes to fuses. Fuses have elected to come up with a strategy for safety to help ensure that you don't put the wrong fuse. For example, if I have a current limiting fuse that accepts current limiting fuses, a non-current limiting fuse will not fit in the holder. Only current limiting fuses will fit in the holder. If I have a fuse block rated for 60 amps, I can't put a 70 amp fuse in this holder. I can put something smaller. This is a 100 amp fuse holder. I could put a 60 amp fuse in here. I could put something smaller, but I'm not going to put a 200 amp fuse in here. And how they do that is they manage the size of the fuses for each of those ranges. And they manage, for example, rejection features. This has a little cutout in it. A non-current limiting fuse won't have that rejection, won't have that cutout. And then the fuse holder itself has a bar in there so that this fits over. And if it's a non-current limiting fuse and you don't have the bar, it won't fit in the holder. So fuses have rejection features, and they have classes just like circuit breakers have frames. So for example, class CC, Charlie Chaplin, has the little dimple at the top and the bottom. You'll see it up there in the picture. And you can typically know where they're applied. Class CF, that is the cube fuse, and that is in a different format, okay? And you can put these in panel boards. We'll talk about holders later. There is the Class G, and we're going to talk about each of these. Class G, higher performance general purpose branch circuit fuse for lighting and appliances and motor branch circuits. You have your RK1s. These are suited for circuits with loads with no like inrush currents, heavy surge for like motors and transformers. You wouldn't use an RK1. An RK5, this is a time delayed overload protection. This is good for motors. So when you hear time delay versus non-time delay or fast acting, you're thinking about the trip curve and what it looks like. So you're either going to have a curve that looks like this, that sags, that would be a non-time delay, or one that has a hump in it, which would be a time delay that would, make sure I do this right, that would go this way and down. Actually, whatever. We'll show you pictures of it. Any case, a time delay fuse is what you would use typically on motors and transformers, something with an inrush. Non-time delay fuse, fast-acting fuses, however you want to call those are those are fuses that don't have a time delay built into the trip curve. Class T for tiny. So these are what you'll typically do, and the reason we call them tiny is they're smaller footprint, smaller overcurrent devices. You'll see these at service entrance, great at limiting short circuit currents. You'll see these in commercial buildings for like those pullouts and things of that nature. So Class Ts are nice because they're compact, they're short, fast acting. They are great for arc flash reduction, great for equipment protection. And you'll notice the rating goes from 1 amp up to 1200 amps. And when I say great for short circuit protection, things like that, I'm talking about the trip curve. The curve for each of these devices are going to be a little different. You'll notice I can get a 600 amp class T, I can get a 600 amp RK5, I can get a 600 amp RK1, I can get a 600 amp class J, and I can't get a 600 amp class L. So I have these three fuses right here, from a class J to a class T to an RK5, all of those I can get into 600 amp fuses. What's going to differ is the trip curves. And that's what's going to help you understand the proper application. But in general, if I've got a motor load, I could use an RK5. I could use a class J. Class J is a single element. Let me get out of the way. Let me get me out of here. Class J is a single element, no intentional time delay, and best applied on circuits free of temporary overloads of motor and transformer surges. Class T, great for critically restricted space. Now, there is, on your Class Js, we have, you can look at the trip curves on the Class J fuses and determine the performance based upon your loads. All right, so and your Class Ls are L for large. L is for large, and those are your big boys and girls. They go from 601 amps up to 6,000 amps. This one here is a Class L. This is a 1200 amp fuse. And remember, you need three of these. In a three-phase system, I need 1, 2, 3. Three of these. All right, nice, heavy, substantial device. You don't want to drop it on your toe. Just saying, not that I've done that. So remember I told you about the standards. So this is your basic dimensions for a class RK1 and RK5. And there's the ferrule sizes. They'll tell you the ferrule size. They'll tell you the length of the body. And you'll notice that from a 1/10 of an amp to a 30 amp, the length of it is 50.8. I guess that's millimeters, 50.8 millimeters. 2 inches, and if it's 35 to 60, it's 3 inches. So they change the length of it, and you'll see the cutoff if you have a 30 amp switch or a 60 amp switch, a 30 amp fuse holder or a 60 amp fuse holder. A 60 amp fuse holder will handle anything from 35 amps up to 60 amps. A 30 amp fuse holder will handle anything from 1/10 of an amp up to 30 amps. Because the dimensions are the same, the size of the ferrule, the length, and you'll notice the rejection feature right up here. And then you know, here is your rejection feature for a this is a specific catalog number, but again, there's the cutoffs: 100, 200, 400, 600. They'll align with the switch standards as well. That's why whenever we say, I know we had this discussion about a 250 amp, I think it was, or we wanted a 225 amp fuse and switch combination, but so many standards would have to change because they don't make a 225 amp switch. You go from a 200 amp switch to a 400 amp switch. So if you wanted a 225 amp fuse, you got to move to a 400 amp switch to be able to put that 225 amp fuse in it. And that's why we got 601. Remember, so the class J goes up to 600. So if I had a 600 amp class J, I could not put that in a class L fuse holder or a class L configuration because a class J goes up to 600. So if I wanted to put a class L fuse, a 600 amp, in a class L application where the holder and whatnot, I could not do it. So we made a 601 to make sure that I can get that into a holder. So people ask, why is there a 601 amp fuse? Well, that's why. It has to deal with being able to put, say, a 600 amp fuse in a specific application in a piece of equipment that's for a class L fuse. I can't do that. So I may want class L performance. So in any case, that's sort of That's sort of the logic behind that. But you'll notice the dimensions of the fuses. So all manufacturers have to meet these dimensions, so that if I buy a Bussmann CC fuse, it'll have the same dimensions as a Mersen CC fuse, as a Littelfuse CC fuse. So all manufacturers of fuses will follow these standards to make sure that the holders can be used with each other's fuses. All right, so let's talk about ratings. Fuses have ratings. And I'm going to grab MobiCam. You'll notice on this fuse here, I've got an ampere rating, 200 amps. So there's the ampere rating. Over here on this side, you'll see it says, for a listed class HKRK5 or RK1 fuse, this fuse may be substituted. There's your manufacturer information. Okay, here we go. This is what I was looking for. It has a interrupting rating of 300,000 amps. So the interrupting rating on this fuse just so happens to be 300,000 amps. And you know how we got, you know what it took to get 300,000 amps interrupting rating on this fuse? We had to build a lab big enough to be able to do it. The value, I guess you would say, of a fuse is the more current you give it, the better it is. It's just the way it is with fuses. You know, fuses love current. The more you give that fuse, the faster it's going to go, the more efficient it is. So this fuse here can interrupt up to 300,000 amps of AC or 100,000 amps of DC. And it has a voltage rating, 600 volt AC, 300 volt DC. If your fuse doesn't have a DC voltage rating, don't use it in DC. Remember, it's got to be listed for the purpose. It has to be used within its rating and its listing. Okay, so let's talk about what happens when you exceed the interrupting rating. Just like anything, when you exceed a rating of an overcurrent protective device, if I apply this fuse into a circuit that has, this is a, I'll make sure I get the numbers right. Don't want to lie to you. This is a 200,000 amp interrupting 600 volt AC fuse. If I put this into an application that had 300,000 amps, I would be exceeding its rating. Now, nothing's going to happen until you call upon it to do something. And if you exceed the rating of a device, we call this achieving an unintended rapid disassembly in the field. You have a basic explosion that can happen because you've exceeded the rating. This can come apart.
This is a serious misapplication.
And it is a serious misapplication to apply a product outside of its ratings. I don't care if it's a current rating or a voltage rating as well. This is the circuit breakers are just as vulnerable to being misapplied as fuses. Now, I will say that there are some good things. He's going to say this is a serious misapplication.
Again, this is a serious misapplication.
Okay, so one of the nice things about this fuse, and I'll give you an example. You know, I've got two fuses here. This is 600 volts AC, 300,000 amps interrupting rating. This is 600 volts AC, 200,000 amps interrupting rating. Do I have to worry about exceeding the interrupting rating when I've got a 300,000 amp interrupting rating fuse or a 200,000 amp interrupting rating fuse? I don't think so. I've got 600 volts. Can I apply this on a 480 volt system? Yes. Can I apply this on a 240 volt system? Yes. 230 volt system? Yes. 230, 231, 480, 481, 482, whatever it takes, as long as I don't exceed 600 volts. So from a fuse perspective, I have to admire their attention to safety with regard to helping people ensure they don't misapply the product. Now, do I make fuses that are of a lower voltage rating? Yes, I do. So this is a KTK5 busman fuse. And I'm just going to look at what the voltage rating is on this. This is an itty bitty boy. Fast acting fuse, KTK 15, and the voltage, and I love these spectacles, 600 volts. All right, so that didn't help. We do have 250 volt rated, and we have lower rated voltage fuses, but it's just sometimes hard to find them. But in any case, most of these fuses are, here's a 250 volt, 250 volt rated fuse. I'll just do a Moby cam on this one as well. This is a 250 volt rated fuse, FRNR 60 amp. This is an energy efficient, what does it say? Amp interrupting rated 200,000 amps. 125 volt DC is 20,000 amps. Okay, so this is a 250 volt. You wouldn't want to apply this fuse on a 480 volt system. That would be ungood. All right. So be mindful that fuses will have a voltage rating. Fuses will have an interrupting rating. Fuses will have a current rating, and just like circuit breakers. So there's your class L, 600 from 601 amps to 6,000 amps, 300,000 amp interrupting rating, time delay, current limiting. Now, how can something be time delay and current limiting? Tom, what are you smoking? What do we mean by that? I'll tell you what we mean by that. And I don't know if I can do this on the fly. I wasn't planning on this, but I'm going to try it. I'm going to try a Moby 1 Kenobi. Let's try a Moby cam. Got a piece of paper. I need a pen. I'm going to help you understand. Yeah, I got a black pen. So here's what we mean by current limiting and time delay. There's my TCC curve. Okay. I'll show you a time delay fuse. So there's your time delay type of fuse. You'll notice I have a little knee up here, and that helps a motor starting curve or transformer inrush, things like that. Now, when we say current limitation doesn't happen until your current gets higher than that number. So over here is your current limiting region. When I say current limiting, I'm not talking about anything on that side of the trip curve. I'm only talking about the performance of this device in that area. Now, let's contrast this with what we call a fast-acting device. A fast-acting device will look something like this. You'll notice there's no knee. So if I have a motor inrush curve and it goes like this, I can accidentally open my my fuse. I might need that little bit of a delay. That's a fast-acting device. It's not intended for motor starting or transformer inrush and things of that nature. I can have current limiting and non-current limiting fast-acting fuses because why? The current limiting region is over here, not over here. So when you hear someone say it's a current limiting time delay fuse, you may go, what are they talking about? You can't have a current limiting time delay fuse. Yes, you can. And the reason it is current limiting is not because of the performance over in this area. The current limiting is over in that area. So be mindful of what that means when people say that. And I'll show you what that gets you. Here's what we mean by current limiting. So this is a typical sine wave of a fault. And there's your asymmetrical sine wave. Remember that first half cycle, it's a doozy. And that steep curve, I want to reduce this peak. I want to take that peak and I want to move it down. And I don't want to have this many cycles flowing. So what do? I apply a current limiting fuse. Because it's way to the right of where my fuse crosses 0.01 seconds, I'm going to very fast, very quickly generate enough heat to hit these pinch points because I'm not in the overload region. Remember, the overload region on this element was over here. I'm going to be in this area. I'm going to hit those pinch points, isolate that fault very fast within a quarter of a cycle. And I'm only going to let through what's highlighted in green. I'm not going to let any of this other waveform pass. All of this is heat, and that first half cycle is magnetic forces. All right, so that first half cycle, this is what I'm doing. There's my current limit. This is what we call a let-through curve. The AB line will tell you, and I'll show you the image. Where's it at? There it is. I love this image. So there's the AB line. If I go up and over, look across the bottom, it says short circuit current. So if I calculated, I don't know, 100,000, well, in this case, if I calculated my available short circuit current of 86,000 amps, if I go to the AB line, it tells me the peak of that first half cycle. So the peak for an RMS current of 86,000 amps, calculated short circuit current, my peak of that first half cycle is going to be 198,000 amps. If I go up to, see where the 800 amp line is, that would be an 800 amp fuse. I take 86,000 amps, I go up to the 800 amp line, I go over to the AB line, or if I keep going all the ways over, that's the peak let through. That would be that peak let through right there. Right there. That, you know, I'm taking the peak from here. That first number, that 100 and some thousand amps was up here. This is my peak let through based on the tables. That's that peak let through right here. All right, so there's my peak. And that would be this number over here. Because I'm basically going up and over. For an 800 amp fuse, I'm determining this value by going up and over. If I get real crazy and I go up, over, and down, that tells me my RMS equivalent. So my RMS equivalent is around 21,000 amps for an 86,000 amp available calculated short circuit current. That's basically what will happen. And if we put this in a lab and we ran a test, these would be the results. My peak of what is resulting would be around 49,000 amps. My RMS value for the resulting current limited event would be 21,000 amps. If I didn't have a fuse in this picture, my peak, like say I had a circuit breaker that lets 30 cycles through, or 2 cycles through, or 3 cycles through, that first half cycle, my peak would be 198,000 amps. That's what puts force in the system. Those are the magnetic forces that occur in a power distribution system. Now, erase all of that, rid of the pen. Let's take a look at an example. So if I have 45,000 amps of available fault current and I put 90 foot of 2-aught conductor and I generate current through it, and I have 1 cycle of current flowing, this is the result. That's 1 cycle of current. That's what that peak does to you. It puts the magnetic forces on the system. Now, what I'm going to show you now is I'm going to put a 200 amp class RK1 fuse. And remember, when I put a 200 amp class RK1 fuse, if I take 26,000 amps and I go up and over, that's going to tell me what my new peak value is going to be. It's going to be much less, and it will result in what you're going to see next. Let's get me out of the way. That is the power of current limitation. And that's what fuses do best. They can reduce the amount of magnetic forces in a power distribution system, which can also reduce incident energy. We can take an event that looks like this. You could take an event that looks just like that, apply a current limiting fuse, and this is the result. So the interesting thing about fuses, when leveraged correctly, I can reduce the magnetic forces, which helps me get higher short circuit current ratings. I can reduce incident energy, which gives me a safer working environment. There's no better and more efficient device than a fuse to achieve those two goals, or none. I don't care what you bring to the table, nothing's going to operate as efficiently as a fuse on those high currents. Now, we started going through the types of fuses, and I'm just going to go really quick down through each of these types of fuses, because I at least want to bring up your awareness. We went over the Class L. Class T, we talked about tiny, up to 1,200 amps, ampere sizes, case sizes, 30, 60, 120, 400, 600, 812. You'll see that those align with fuse switch sizes or fuse holder sizes. 200,000 amp interrupting, current limiting. They've got rejection features or size rejecting. The best space saving of any of these devices. Class H, these are 250 volt, 600 volt, 1/8 of an amp to 600 amps. These are your non-current limiting device. There's no time delay, non-time delay, non-current limiting. There's no rejection features on it. You'll see those blades. There are no slots in those blades. You'll see these on HVAC, light commercial. Your goal, in my opinion, is to, when you see these Class H fuses, try to get them converted over to a current limiting and fast acting device, current limiting device, which will have the rejection features like that on the blade instead of that on the blade. And the reason is they'll give you better performance, lower incident energy, Higher interrupting ratings, the whole bit. That's only 50,000 amp interrupting rating. What else? Okay. And then you'll need rejection clips and things of that nature. And we'll talk about those in another session. This is your 250 volts, 600 volts, 1/10 of an amp, the 600 amps, 200,000 amp interrupting rating, RK5 fuses, dual element time delay, good current limitation. Remember, current limitation, high currents. And you can put these on feeders and branch circuits. Good for motor starting applications, all that good stuff. RK1, dual element time delay, better current limitation, less time delay than an RK5. Again, feeders, branch circuits. Primary. When you hear time delay, you're looking at that overload region. Your class J's, 1 amp to a 600 amp, smaller than an RK1, RK5, so your switches are going to be smaller, your holders are going to be smaller, gives you more space, fast acting. Feeder and branch circuits, OEMs use those. Type 2 protection, if you remember, you're leveraging the fast acting current limitation of this to provide no damage on short circuits inside that equipment. This is your cube fuse, different footprint, square footprint, goes into a different type of holders, square holders. But they're basically class J performance. So the same element, than a class J fuse, just put in a different footprint. Very nice from a panel board perspective. We make panel boards with these things. Finger safe solutions. Don't have to take the dead front off to change a fuse. Very attractive. Charlie Chaplin's class CC. You'll know these by the little dimples at the end. That's a rejection feature. Current limiting up to 200,000 amp interrupting rating, 600 volts. All right, and they'll have their own handle. You know the two. You know these Edison fuses, Edison-based type fuses. They still sell these for some appliances. Will still use them. And again, NEC 240.51b permits the use of plug fuses of the Edison-based type to be used only for replacements in existing installations. So, still permitted for replacements. And just like in circuit breakers, we have supplementary overcurrent protected devices. These devices are not branch circuit rated. They're listed to be used in another application. So they're typically recognized components within other, in control and whatnot. These are not branch circuit devices, not suitable for use as branch circuit protection. We talked about the ratings. You'll have the catalog number. You'll have the ampacity or the amp rating of the fuse, the voltage rating of the fuse. Remember, never use an AC rated only fuse on a DC system unless you see DC and AC. We already looked at that. And they will have an interrupting rating. Fuse holders, again, we saw that. Now what's nice about this fuse holder is it has the lockout tag out. You can take the fuse out, put the cover on, and lock and tag it out. It also has an indicator on the front, so it tells you when this fuse is opened. This LED will glow when the fuse is opened. You can get a lot of flexibility in holders, DIN rail mounted, fixed mounted, all that good stuff. That's a discussion for another day. We already talked about current limitation. And I will mention quickly and briefly, there are high-speed fuses that are used in drive applications and things of that nature. They have smaller weak points. They have you don't size a high-speed fuse based upon an ampere rating. You size a high-speed fuse based upon the amount of energy that you will let through. You'll see the construction is typically a ceramic body. They're either going to be round or they might be they'll be round cylindrical. They could be square. I think you've probably seen high-speed fuses that are square and they're porcelain, ceramic, or a ceramic body. They'll have different mounting capabilities. You'll typically find these in OEM applications. And again, you don't size these fuses based upon the ampere rating of a conductor or anything. You size these fuses based upon the amount of energy that will be let through. It's a different way to size them. And again, the fuse curves, and a lot of these fuses are not designed to be used in overload applications at all. You don't want to operate this fuse in the dashed line area above this A line right up here. You don't want to operate these fuses in their overload region. They are there for reduction of damage to equipment based upon let through energy. I'm telling you, my first experience with sizing one of these, we had an application with an OEM who wanted they needed a replacement fuse, a high-speed fuse that was no longer made. And my brain went into, well, what's the ampere rating of the circuit? What is the conductor that you're trying to protect? And they said, no, here's how many joules I can't let through. I have to be less than this much energy. And that's how you pick these fuses. So, all right. So we went through fuses, went through a little bit of fusology. Hopefully you understand how fuses operate. Hopefully you understand a little bit about their ratings. And again, this is the first of probably a series in fuses, associated with fuses. All righty. Don't forget, please subscribe to the YouTube channel. Become an IAEI member. I'm counting on you, the organization. We're going to be bringing more and more value to IAEI members only through online educational resources and events that are available only to IAEI members. So you're going to want to not miss any of those and become an IAEI member to receive the benefits. Thank you for your attention this entire session. If you're holding in till right now, I really appreciate your attention. I appreciate your desire to learn, and I appreciate what you do for the electrical industry, because every moment you improve your skills, you help the electrical industry and you help electrical safety. So my time is up. Until next week, I look forward to seeing you all right here on IAEI News Live next Tuesday, same time. Take care, stay safe, God bless, and please stay healthy.